I would like to welcome everyone to this series of lectures in which we will be discussing the nonlinear analysis from the viewpoint of degree theory. In particular, we will be interested in the Brouwer degree theories, such as a classical local Brouwer degree, and later on we will introduce the notion of the equivariant Brouwer degree for studying nonlinear differential equations with symmetries. Let me first explain that the notion of the degree is associated with the name of this, so let's write his name properly. This is Luitzen Egbertus Jan Brouwer, a Dutch mathematician who lived between 1881 and 1966. In the year 1910, he published a famous work in which he described an invariant that he called the degree, and this was a topological invariant, so this will be topological invariant to classify the homotopy classes of the continuous maps between two spheres, It turned out that this degree is an integer number. So it was published in 1911. So that's the famous work that initiated the whole idea of using the degree theory in the study of nonlinear equations. And I will talk later about the bibliographical facts and how our presentation is, connected to the original work by Brouwer. But for a moment, my goal will be different. I would like to introduce the local Brouwer degree theory, first using the axiomatic approach. So let me write it and let me start our lecture. So this is local Brouwer degree and it is axiomatic approach. So let's begin with the basic notions. So first, let me indicate that by this symbol V, I will be denoting usual Euclidean space, and we can start with the dimension 0. That's 0 dimensional, as simple as possible, and then 1, 2, and so on. So that means, in this case, Rn is equipped with the Euclidean norm, and also we have here the notion of the open ball, center x naught. So this will be open ball, the set of all x's in V, such that x minus x naught smaller than r. So that is the notion that this will be open ball. This is open ball in V of radius r, center at x naught. And our attention will be given to the following objects. So first of all, assume that f from V to V is a map. So this is a continuous map. And for this continuous map, and assume that omega, let's say like that, this is an open bounded set, and we will say also that this map and this particular set is maybe called this definition. So let me erase it first. Okay. So definition. Such a pair f omega described above is said to be admissible if f of x is not equal to 0 for x's belonging to boundary of omega, to the boundary of omega. So in such a case, we will also say that the map f is omega admissible. Is omega admissible. So, okay, so that's our definition. So in certain way you can imagine that this one is our Rn, that's Rn, a plane. So here we have here a map that goes from Rn to Rn. So this is F, and this is going to another copy of the same space. So this is my V, this is my V, and then of course I have here the omega, some set omega. This is my omega, and we know that the solutions, and we are interested to the solutions of the equation f of x is equal to 0, and we know that there are two types of solutions, so this is our 0. Some of those solutions are inside omega, inside means in the interior, means in omega, and then some of them are outside. And the condition of admissibility means that the boundary is a separation between these two types of solutions, those types of solutions. So we will be interested in the solutions that are located inside the set of omega. And basically the degree theory is the kind of a, let's say, invariant, which will be expressed by an integer number that will be counting, in some sense, algebraically, the solutions inside a given omega set. So, what else we will say? We also say that one admissible pair f0 omega is homotopic maybe put it in red because we want to make it more clear, homotopic to another pair, call it f1 omega, if there exists a continuous map and call this map H, which will be of course H because it's going to be a homotopy. 0, 1 times V to V. So that's exactly homotopy. That map means T here, parameter T. First parameter T means the parameter belonging to 0, 1 is the deformation parameter, which allows us to deform one map and to another one, such that, such that we can write it down, A H of T x is not equal to 0 for all x belonging to the boundary of omega. So that means, this means admissibility, admissible, okay. This means that H, put it like this, HT of T1, and this will be HT, and put here dot, is omega admissible for every T belonging to 0, 1. So of course, T belongs to the 0, 1. And then the second condition is B, that in this case I'm using this notation, that H of 0 of x is equal to f of 0 of x, and H of 1 of x is equal f1 of x for every x belonging to V. So that means the H is actually a transformation, continuous transformation. It transforms f0 to f1. In this case, H will be called omega admissible homotopy. Omega admissible homotopy. And of course, notice that the above relation of homotopy which we can denote it like this, f0 omega, and that's the homotopic to f1 omega, is an equivalence relation. It's an equivalence relation. Couple of examples. So maybe like this example. First, the most trivial example. Consider R0, which is just simply zero-dimensional space. So that means there is only one non-empty, let's say one non-empty set here. So if you notice that in this case, if omega is equal to 0, so clearly this omega equals to 0 is a bounded set. It's a bounded set in this space. It's open, and of course the boundary of omega in this case is empty. And any map from R0 to R0 must be identity, means the 0 goes to 0, is admissible. So this is omega admissible. So that's my first trivial example of admissible pair. The second one, take Rn and take omega being an empty set, and f going from So V is our Rn. So in this case goes from V to V. Any continuous map is any continuous map. Then clearly F omega is also admissible pair. Yeah, that's interesting. So, all possible admissible pairs, there can be many. So let me maybe make a notation, introduce the notation. So for a given space, in this case V equals Rn, so this Euclidean space, we put M, and I put here V. This is the set of all F omega such that F is from V to V, omega is a subset of V. This is bounded and open, so that one is continuous, open, bounded. And the third one, F omega, is admissible. So this is the set. Something happened. Sorry. Something happened. So this is the set of all possible admissible pairs in V. Defined for maps on V and the open sets in V. Open bounded sets in V. Then we also put, and we define the V, so that means M without V. This is the union over all Euclidean space, and I put here this M of V. So in such a case, M is the collection of all admissible pairs in Euclidean space. Euclidean space is V. So that's exactly the notation that we need, and now we will introduce the Brouwer local degree by an axiomatic definition. So let's us introduce it. So let's put it like this: definition. A function and in this case I denote this function by degree, and it goes from M to integer numbers, is called a, let's maybe put it in brackets, local Brouwer degree. Sorry. If it satisfies the following three conditions. So the conditions, call this one P1, or property, we can say. First one is called the additivity. And let's put it like this. Let for, okay, any admissible pair F omega and two open subsets, omega 1 and omega 2, contained in omega, so two open subsets satisfying the properties such that we have here, let's write it down, F, okay, omega 1 is disjoint with omega 2, and F minus 1 of 0 intersection omega is contained in omega 1 union omega 2, we have, and here degree of this pair on omega must be the same as the degree of F on omega 1 plus degree of F on omega 2. So the picture for this property looks like that. So this is our omega. Then you have your two other sets, like omega 1, omega 2, and the solutions are either here in the first one or in the second one, not in between. In such a case, you can see that in this, that this condition is just telling you that it's a kind, that the degree is a kind of an algebraic count that is counting first the solutions in the omega 1, so that is this one, and then solution in omega 2, and they add up the results, which gives you the degree of omega, in omega of M. So this is the first property. The second property is the P2, which will be called the homotopy property, put it like this, homotopy. For any admissible pairs this will be F omega. So call this one 0 and take F1 omega belonging to N. So omega is the same for both. We have, it's okay, sorry, such that F0 omega is homotopic to F1 omega. We have that degree of F0 of omega is equal to the degree of F1 on omega. So that's the second. So basically, this particular result here, that means this property tells you that the deformation, continuous deformation of one map onto another map is not really changing the degree. And sometimes you can think about this property as the computational property because it allows you to take something which is complicated deform it to something much simpler, for which you can actually use the techniques and compute this degree effectively. And the last one is called the normalization. And this property simply says for any x naught belonging to V, for any point x naught belonging to V and omega contained in V, open bounded set such that x naught does not belong to the boundary of omega, we have that the degree of the identity maps shifted by x naught on omega is simply equal 1 if x naught belongs to omega, and 0 if x naught does not belong to omega. Of course, it cannot be on the boundary. So that map, identity map, is basically the admissible, and look what it is. This represents the simplest possible equation you can imagine. X is equal to x naught. You are looking for solutions in omega. So if you see that if you x naught is in omega, so that means the solution to this equation is in omega. How many solutions? Solutions 1. So that property, normalization, is basically also telling you that the degree is a non-trivial. That means sometimes it can be 0, sometimes it can be not zero number. So these three properties actually turns out to be sufficient, and we will derive from these three properties an analytic formula, and this analytic formula will be next used in order to show that it actually defines effectively an invariant degree as an invariant satisfying all the required properties. This approach is definitely different than the original idea of Brouwer. However, we will mention how this is connected to the homotopy classes on the spheres, and this will be done later, but for a moment we concentrate on the simplicity and in particular the properties of the degree. In this case, provide us with sufficient, let's say, tools in order to not only compute it but also use it effectively in many possible situations. Let me point out that our goal is not exactly the Brouwer degree. That's a theory that is in existence for more than 100 years, but it is the version of the Brouwer degree which in a certain way is derived from the Brouwer degree itself in order to study the symmetric equations, the equations admitting a group of symmetries. In such a case, this Brouwer degree that we are aiming at will be called the equivariant Brouwer degree, and of course, understanding something on this particular level will require some knowledge about the original Brouwer degree. That's why we will spend some time studying first the local Brouwer degree, its properties, and also some of the applications also to maybe just simply to simple problems in mathematics or algebra or anything. Okay, let's say we'll show it later. So we will concentrate on on this path in order to achieve the goal of going to the more, let's say, advanced type of the degree. So maybe the simple consequences. So let's see, proposition. So proposition, maybe write it down, proposition. Suppose degree, we have a given degree, so we assume here that such a degree exists. Suppose this is a degree, suppose is a degree. Then we have additional property, the following. Additional properties. And first one, so call it like this, P4, and this will be called existence property. If degree of f omega is not equal to 0, then there exists an x naught belonging to omega such that f of x naught is equal to 0. So that means the solution, there exists a solution to the equation f of x equal to 0 in omega. In omega. So there exists a solution. So maybe, let's go to the next page. So the secondary, P5, is the so-called excision property. Excision property. And this is maybe in certain way a simple adaptation of the additivity theory to the following statement. If f omega belongs to M and omega 1 contained, 1 is contained in omega, an open set such that f minus 1 of 0 on omega is contained in omega 1, then we have that the degree of f of omega is equal to the degree of f omega 1. So again, the picture here we have here omega, and then we have a smaller omega 1. All the solutions are here, not in between these two sets, not here, not here, here. Then we have this equality. That means simply that you can change the size of omega and the degree does not change. And then you have next is a P6. And it's called the continuity. I will explain why it is called continuity. Continuity property. And this simply says like this: if you have here f1, okay, maybe f0 omega, and this one is f1 of omega, are two admissible pairs. Of course, notice that this is the same omega, so that means it's on the same space, such that, and I can specify it here. What is that? Such that supremum of x on the, let's say like this, of x belonging to, okay, boundary of omega. and call this, take the norm of f of x minus, I should use f0 of x minus f1 of x is strictly smaller than infimum. Of course, this supremum is maximum. This infimum is minimum. That's because this says that we are dealing with a compass. So this is f0 of x, one of them, just one of, take one of them. 10, we have here the degree of f0 omega is equal to the degree of f1 of omega. So why it is called the continuity property? Because in certain way, if you notice that here, maybe let's go to the next one and then in the little larger context we explain it, and then you have here a property which is called the boundary property. Namely, if you have here that f0 omega and f1 of omega belongs to M are such that f0 of x is equal to f1 of x for every x belonging to the boundary, then exactly the same conclusion is satisfied. That means the degree of f0 omega is the same as the degree of f1 omega. So now maybe let's do the explanation why it is called the continuity and boundary. Boundary because they coincide on the boundary, and continuity is related to this fact. So let's see, remark. If f of omega belongs to n, so that means also that f is transforming a boundary of omega to v minus 0 boundary. So the boundary condition tells you that any two maps such that they have the same values, so they will define, and you see if you have f0, fn1, they define to you one unique map on the boundary, and that's enough to determine the degree of this one. So in certain way, in such a case, if you take the condition number 6, then you have here, if you f1 restricted to the, if f1 and f, maybe later down here, if f1 restricted to the boundary and f2 restricted to the boundary are close to each other, maybe sufficiently close, are sufficiently close in the space of continuous function on the boundary to V. So this is the space of continuous functions or maps equipped with the norm that is of course the supremum norm. 10, their degrees coincide. Then their degrees coincide. So this 7, let's say, well, now we have 7 properties, maybe indicate the proofs very quickly because they are all trivial. So the proofs are very simple. So if you go to the P4, so of course you notice that if you write it down, degree of f of omega is not equal to 0 implies that that the equation that f of x is equal to 0 for some, so maybe write it down using quantifiers, then there exists an x belonging to omega such that f of x is equal to 0. So of course this statement is equivalent just to say, so this is equivalent to show that if for every x belonging to omega, we have here f of x is different than 0, so then we are getting here the degree of f of omega is equal to 0. So that's what we need to show. And in order to show it, so let's do it. So what do I have here? So indeed, degree of f on omega can be written as the same as degree of f of empty set plus degree of f of empty set. By additivity. So in our case, this one is our omega 1, this one is omega 2, and it's very easy to verify that the conditions specified in the P1 are definitely satisfied, so we are getting that guy. And clearly, degree of f on empty set is equal to 0. Is it? Why? Why? Because, put it here, maybe it makes sense to do the trivial. Again, by the additivity. You can do the same. And that implies that the degree of is equal to 0 because you just cancel 1 and 1. And you are getting 0. Yes. So that must be equal to 0. Done. And of course, the excision is also trivial because now we can write the excision. So now the excision, so this is P7, which one is P5, sorry, P5. P5, then we have here for the P5, we are getting f omega, and by additivity again with the empty set, one empty set, so this will be f omega 1 plus, sorry, I must squeeze it better, equals degree of f omega 1 plus degree f empty set, but to empty set we already know is 0, so this is equal to the degree f omega 1 plus 0, so that means equal degree of f of omega 1. Done. Done. And then let's go and continuity. So P6. So define the homotopy. And I put here HTX is equal TF0 of x plus 1 minus TF1 of x, and notice this homotopy, we'll refer to this type of homotopy as a linear homotopy because it basically shows you that a value of f0 x and the value of f1 x are connected by line integrals, so this is called linear homotopy. And notice that h of tx is different to 0 for x belonging to omega boundary and t belonging to 0, 1. Indeed, we have, and let's write it down, norm of h tx, norm of h tx, so let's write it down, this is equal tf0 of x minus 1 minus tf1 of x. Yeah, let's see where is f0. Yeah, I need to change. Yeah, I let me replace that one and that one like that, so this will be 1 and this will be 0. Yeah, why not? And just to make a simple adjustment in order to fit the definition, the conditions there. So now we can rewrite it down. So this is equal to f1 f0 of x and minus t, and this will be f0 of x minus f1 of x. Oh, I think this is correct. So let me check it. Minus 1, so this is minus 1, and this is plus t, so this is plus t, so minus I. Okay, it is changed a little, but that's the same. And then larger equal, and what do I get here? I'm getting f0 of x minus t, and this will be f0 of x minus f1 of x. And since t is in 0, 1, I can write it again, f0 of x minus f0 of x minus f1 of x. And then we are getting here that that one is larger equal again, and this will be infimum of f0 of x, x belongs to the boundary of x, minus supremum, and this is f0 of x minus f1 of x. And that's our assumption, so it's larger than 0. If it's larger than 0, it cannot be 0. So, thus, by property P2, homotopy property, by the homotopy property, we have here that the degree of f0 omega is equal to the degree of f1 omega. Of course, in order to prove P7, in order to prove P7 is a trivial consequence of P6. So this is P6. So we got it proved. Okay, and also the first elementary properties that can be easily deduced of the Brouwer degree, that can be easily deduced from the three initial properties. We usually say that these first three properties, P1, P2, P3, are the axioms of the Brouwer degree, local Brouwer degree. And once you learn the axioms, you don't need to know any topology, any homotopy theory, in order to have kind of an understanding what is the degree. You just use these axioms and derived all other properties and apply the degree effectively in an analytic way. So maybe we put something like a little subsections, and this will be called the degree of linear isomorphisms linear isomorphisms. So what are these degrees? So let's say like this. Suppose, maybe let's start like this. For a space V is equal Rn, we denote by G, L, and R the set of all linear isomorphisms A that goes from Rn to Rn. Clearly, you can think about the GLN, which is called the general linear group of Rn. So this group. Satisfies the properties basically that since we assume that Rn is a Euclidean space, so we have chosen the standard basis in this space, and now every matrix can be, with respect to this chosen basis, represented as a matrix, n by n, a matrix. So that means simply you can think about it, so which can be identified with n by n invertible matrices. Invertible matrices. So, in certain way, if you look at that one, we can say I have here Rn. This is the set of all matrices, so put it like that. A is a linear isomorphism. So that put it like this, A linear, and since it can be represented as a matrix, determinant of A not equal to 0. So this is determinant of A is not. So we have two conditions, one and the second one. So the general linear group can be characterized by these two conditions. So now it is interesting fact. So let's put it like this. Proposition. I'm not going to prove it. I'm not only going to argue for the proof. Proposition. We have for n larger than 0 that GL and R can be represented as a GL and R with plus, and that one is equal to the GL minus NR. So where, and let me write it down, GL and plus minus, maybe write it down, plus minus NR, maybe just be specific, NR is equal to the set of all matrices GL and R such that determinant of A is positive and GL minus and R is equal to the set of all matrices with the determinant A negative. So there is No need to prove anything because it comes from the definition of the GL and R. But the next statement is actually where GL plus and R and GL minus and R are path connected. That's what needs to be proved. Path connected. This path connected. That means it is possible to connect any matrix. Maybe let's say like this. Notice, put it like this, put it like under. Notice that the statement tells you that any matrix A in GL plus and R can be connected to the matrix, identity matrix. Okay, so what's identity? This is just a matrix 1, 1, 1, 0, 0. It's not nice. Like this. 1, 1, 1, 0, 0. And the other one, and if A belongs to the GL minus N R can be connected by continuous path to this matrix. I call that matrix J. So J is different in identities. First one is minus 1, after then identity. Everything else on the diagonal is identity, except the first one, which is minus 1. So that's the only statement that we need to prove, that it's possible to connect it. So the idea of the proof is, proof, just simply, idea is based on the idea. I'm not going to do it. This is not necessary because everybody can basically understand it by properly translating the canonical Jordan form for real matrices into the real canonical Jordan form. So how it is done? So remember, if matrix A belongs to the GL and R, so you can look at this matrix as a matrix which is complex, because a real number is a complex number, so a real matrix is also a complex matrix. So in such a case, you can write it down that this matrix has the Jordan canonical form. So this is Jordan canonical form. And what does it mean? Then you have here eigenvalues. So put it like this. First eigenvalue is lambda 1. But remember, if you have an eigenvalue lambda for a real matrix, and if it is not a real number, suppose you have here a complex eigenvalue. So in such a case, you have two eigenvalues actually, because the conjugate in this case will be also maybe I should be more clear. So lambda 1 and conjugate lambda 1 bar. Be also eigenvalue, because any real polynomial, if it has the polynomial, gives you two solutions, two complex solutions. So then you can say, okay, I'm getting here complex values, and then I'm having, for example, the last one complex will be k, and then you have here that one, and after that we have only real eigenvalues. So let's say like this, lambda, and this will be mu L, and then here I put, there may be something else, that means the matrix is triangular. So mu I are real numbers and the lambda j are complex roots. Those are the eigenvalues. Those are real eigenvalues and complex. So this is the Jordan canonical form. It is a triangular matrix. Triangular matrix. So now let me look at that one. You should understand that you can still return. So in this case, if you have, for example, this little block here, any of those blocks, put it like this, little block like that. So put it like this. This is lambda, lambda. There is something standing here. So in such a case, this, let's start with just simply this case, nothing else. So this is lambda and this is bar. So this particular matrix, if it is literally like this, A plus B, will correspond. You can take the eigen vectors here, the eigenvectors here for this one, and take the real part and imaginary part and make a decomposition of the real space into such a way that this little block will be corresponding to this particular block. Namely, this will be A, this will be A, and this will be minus B and B. So such a block will be given by that particular block matrix. So in black matrix. So in other words, the Jordan matrix, canonical matrix for real matrices can be written like this. So we have here these blocks corresponding to the complex eigenvalues, and then you have here the last complex eigenvalues, and after that we have here real eigenvalues, which we don't need to do anything. They are good. So this will be L. And here we have here, call this like this, A1 minus B1, B1, A1, and then you have here A2 minus B2, and then you have here A2, B2, and this will be AK minus BK, and this is BK, AK, and there may be something. This is triangular matrix again, and then you can go down, and here is 0. So the deformation, the path that allows you to deform, is kind of very easy. This is kind of an easy path. First, you get rid of the triangular part. You put here parameter t for the homotopy and remove anything that is in the upper triangular matrix. Then you notice that any matrix of this form, that if you write it down A, because A squared plus B squared is larger than 0, then you have the matrix A, B, B, A, can be written using this one. So here we have here like this, R cosine certain alpha. So namely, write it down, maybe A plus IB is equal to REI alpha. And then you have here R minus R sine alpha, and this will be R sine alpha, R cosine alpha, and you can easily see that you can transform this one using homotopy, let's say reducing R to 1, and by using the rotations to the matrix 1, 1, 0, 0. So that shows you that this matrix, by a simple homotopy, can be connected to the identity matrix, identity matrix on this block. So this will be identity. So you can easily remark that here you are getting here every of those blocks will be mapped into the identity. And then if you have here eigenvalue which is positive, then this will be called, you can reduce it easily by shrinking it to 1. And if eigenvalue is negative, if this is negative, then it goes to minus 1. So after some deformations, you can see that you can regroup them, just simply change the basis, regroup them in an appropriate way, in such a way that put here all the negative at the top, maybe. So those are the negatives, so let me a second. Those are the negative, and then we have positive. So the next step in this deformation is that if you have here a block consisting of two numbers minus 1, let's say like that, so you have here like this minus 1, 0, 0, then again you can use the homotopy exactly, cosine homotopy which will be exactly cosine of t sine of t with minus sine of t cosine of t, and you can see that cosine of pi is 1, 1, minus 1, and sine is 0, 0, so this means for t belonging to pi it is the first matrix, for t belonging to so for t equals pi, okay. For t is equal 0, I'm getting the first matrix. For t equals pi, you are getting the first matrix. For t equals 0, I'm getting the identity matrix. So this will be homotopy to identity. This is A, and this will be, this is A1, and this will be identity. So that gives you the homotopy. So of course, if the number of the elements standing on this portion of the diagonal is even, then this will be identity matrix. If this is not even, then we can leave the top one and reduce all others to identity. So we'll be getting the matrix J. And that basically the idea behind the proof of this statement. And there is of course there is a possibility to do it in the more detailed way, but for us what is the most important is that from this particular statement we have immediate conclusions. So put it like this: theorem, which will be kind of important. Again, we have still assumed let degree from M to Z be a degree, and assume that A belongs to the GL and R, 10 degree of A on omega is equal signum of determinant of A, where omega is any open bounded neighborhood of 0. So that's what we are needing to do it. And proof of this statement is based on two steps. Proof: if determinant of A is positive, then A is omega admissibly homotopic to identity. So by the property P3, which means homotopy property, degree of A and omega is equal to 1. And the other one, if if A is omega, okay, maybe like this, is such that determinant of A is negative, then A is homotopic to J omega admissibly, homotopic to J, which is exactly -1, after that 1, 1, 0, 0. We claim that the degree of J on omega is equal to -1. So the proof is needed. So this one, proof of this statement. So we need to prove this statement. We can prove of that particular statement. So let me do it, and basically it is a very simple fact, namely, first of all, we need to consider a special map. So let me do the following. So maybe like this. Since by excision property, excision property, we have only, remember, J of x is equal to 0 if and only if x is equal to 0. We will assume that my omega here is equal to the ball of the radius 1/2 equals to 0. Very good. Now, suppose that omega naught is equal to the ball of the radius 2 and defined the following omega 0 admissible homotopy. So in this case, this homotopy looks like that. So I have here H 0, 1 times Rn to Rn, and H of Tx will be given by the formula. So let me write it down like that. So this is kind of important. I put here 1 minus t plus t, and I put here a function phi of x, and this will be x1. So we have here x1. So x is equal to x1, x2, xn. So here we have here x is equal x1, x2, xn transposed belonging to Rn. So I put here phi 1 of x. I will explain it. So x2, xn, n, and here I'm getting here that this function phi is kind of easy to imagine, namely this will be put here like this. This is -1, this will be -2, this is my 1, this is my 1, and the function looks like that. So it will be value 1 here, value 1, and then it goes here that way, and then no, that way, halfway, and then I change it like that, so it goes to the 0. Oh, that. Very good. And put it clearly, and we put it like x naught. Also x naught will be a given, not maybe not this one, x naught will be the point minus 1, 1 and 1 transpose. So notice this is clear. This is omega not admissible homotopy. So this is omega not admissible homotopy. Yes, it is admissible because ball is big, so this is in minus 2, 1, so that's a ball. And of course, you can see immediately that h0, h0 of x is nothing else than the map that looks like that. So it will be 0, so this will be 0, so this will be map that gives you value 1, and this will be x2, and this one is xn transpose, which is never equal to 0, so you clearly see that this implies that the degree of h0 on omega naught is equal to 0. On the other hand, we have, so let's write it down. So let's write it down. The 0 is equal degree of h0 on the ball omega 0, so it is of radius 2. So that one is equal to. And then I say, okay, but where are the zeros here? So here we have 2 zeros. So if I say that h1, this is the degree of h1 of omega 0, so h1 of x is equal to 0 if and only if x is equal either 0 or x is equal of x naught that is specified here. Here. Should use the right column. Here. So this is my x naught. So I can take two balls, two neighborhoods of that one. So namely, I can put it down equals and continue here, so put it like a bracket. So this will be equal, this will be equal, and I put here degree of h1 on omega, put it number 1 plus degree of h1 on, so this is not degree of h1 omega 2. So what is omega 1? So omega 1, I take the ball. So look at the picture again. So this will be this ball. 1/2, 1/2, 1/2. So let's write it down. Omega 1 is equal ball of the radius 1/2 around x naught. And omega 2 will be the ball of the radius 1/2 of 0. And that exactly, yeah, that's how it is. And that's exactly here. So now you can see that one of the points belongs here, another belongs there, the solutions of the equation. So I can continue and I can write it down. This is the degree of h on, but what is h on omega 1? On omega 1, you can see h, here is the identity, this is the identity, but here will be 1. So what do I get here as a 1? This will be minus 1. This here is minus 1. So I'm getting here that this is equal j. This is nothing else than j. And that will be plus x naught on omega 1. And the second one is the degree of identity. Here is the identity on omega 2. That's the identity. And this is the identity. This is identity. This is minus identity plus x naught here. So the first one by the property P3 is equal to 1. So I'm getting this one is equal. So this one is equal, so this is the degree. And I can again expand it to the omega naught. Why? Because by excision property. So this is by excision. Excision. And that one is 1. So now I can introduce additional homotopy, put here t, and t belongs to 0 and 1. So this homotopy, let's be more specific. So this will be equal, and I can add the homotopy parameter, degree j plus tx naught, and this will be omega. And then by homotopy property, the P2, we're getting, this is the degree of j on omega. 0, plus 1 is equal by the P2 degree of j omega 0 plus 1, and that of course implies that the degree of j omega 0 is equal to minus 1, and we achieved the goal. We showed that indeed that the degree of any isomorphism on omega is equal to signum of determinant of A, and I think that's enough for one lecture.